Come here, boy. Come here, boy. You big stinky boy. How you doing, big stinky boy? Yeah, it's almost time to start teaching, Mr. Bugs. You're gonna start teaching soon. It's almost time. Sweet baby boy. I'm gonna wait till there's a few more people here. Yeah, we only got 6 people. What do you smell? You hear peoples? Little doggos? Am I... Why are there so few people? What's happening, buggers? Am I too early? Let me try. What the heck, man? Oh no, this class already started, man. What the heck, dude? Where is everyone? Alright, I'm going to start in 1 minute. Whether there's peoples or not. Yeah, oh, you're so precious. You're so precious, boy. Buggers. Can I get you num num? No? Okay. Okay, I'll put you down. All right, I'm going to go ahead and get started. Hello, class. I'm going to try to keep this lesson to about 20 minutes, and then I'll check in with you guys in the Zoom room. So, what are we talking about today? Well, we are going to be talking about energy and the mass spring system. And this is our lesson, or our topic for the entire week. Okay. So just to remind you what a mass spring system is, it's you got a wall, and you've got a frictionless floor, all right, and you've got a mass M that is at rest, okay, or not at rest, but it's just sitting there for now. And then there's a spring of stiffness K, which is attached to it. Now, this, where the mass is right now, I am going to call that x equals 0. And that is the equilibrium position. Okay, so what does that mean to be the equilibrium position? Well, at the equilibrium position, this spring is neither stretched nor compressed. Okay, so the spring is just sitting at its natural length. Okay, and because it's at its natural length, that means that the force, the elastic force, is going to be 0. Okay, and so if you start out with the mass at the equilibrium position, it's just going to stay there forever. Okay, just like for a pendulum, the equilibrium position is when it's straight up and down. If you take a pendulum and you just leave it there, and you just put it vertical, and you just leave it, it's going to stay vertical, right? So the meaning of the equilibrium position is it's the spot where if you put it there, if you start it there, it will just stay there forever, okay? But we're not going to do that for this lesson. We are going to take the mass and we are going to pull it to the right by some amount, okay? And so this right here, the amount that we pull it, so we are going to pull right, pull the mass right, and release from rest. Okay. I'm going to draw another guiding line on the symmetrical line on the opposite side. Okay. So because we're releasing it from rest, okay, the mass is never going to be able to go right at this point. So this is actually the amplitude. Okay, it's released from rest. Now, obviously the spring is stretched at this point. Okay, so a little bit later what's going to happen is, because the spring is stretched, it's going to pull the mass to the left. So it's going to pull it maybe to right here. Okay, now because it's pulling to the left, the mass is going to start to pick up speed. Okay. Then it's going to arrive at its equilibrium position. But here's the thing. It's picking up speed for this entire, as it goes from here to here, it's been picking up speed. So it's going to have a ton of speed at that point. Okay? And because of that, it's not going to stay at equilibrium. It's going to pass through. It passes through equilibrium because of its inertia. So it just keeps going because it arrived at equilibrium when it was moving. If it had arrived at equilibrium with no speed, then it would just stay there forever. But because it arrives with speed, it's going to go all the way through. And then it's going to pass through equilibrium. And once it passes through equilibrium, now the spring is starting to get compressed. And so because the spring is compressed, that is going to slow the mass down. Now it's still moving to the left, but it's going to be slower. Okay? And then eventually it'll reach its leftmost point, where it has fully compressed the spring and it has no velocity whatsoever. That point is going to be at x equals negative a. By the way, this is time 0, and then we're just having time go on, going downward. Okay. So now it's at rest, and because it's at rest, and the spring is compressed, the spring is going to be able to start pushing it back in the other direction. Okay. So now it's going to gain speed going to the right. It's going to pass through equilibrium with a lot of speed, but it's not going to stay at equilibrium because it arrived at equilibrium moving. So it moves through equilibrium because of its inertia. All right. And then it's going to, once it passes through equilibrium, then the spring is going to start to slow it down. And then it is going to stop at the same point it stopped right here. So what we have shown is a complete period of the motion of the mass in the mass spring system. All right. So what we want to do is we want to analyze this in terms of energy. All right. And energy is conserved in the mass spring system. All right. So what is the energy when we are right here at the extreme point? Well, the mass is not moving, so it has no kinetic energy, but the spring is stretched, so it has elastic potential energy, which is given by the formula 1/2 kx squared, and its x-coordinate at the extreme point is A. All right? So that is the energy when it is at the extreme point. All right? Now, if we're right here, we can see that the spring is still stretched. Okay? The spring is still stretched. So we have, but it's not stretched as much as it was right here. So we have some elastic potential energy, but then we also have some motion happening, so we have some kinetic energy as well. So here the energy is going to be 1/2 kx squared plus 1/2 mv squared. All right. Now here, the mass is passing through equilibrium. All right. And because it's passing through equilibrium, it has x equals 0. The formula for elastic potential energy is 1/2 kx squared. So if x equals 0, we have no elastic potential energy, and therefore we have all kinetic energy. Now, if we have all kinetic energy, that means if all of your energy is kinetic, then that means you're going as fast as you could go. Because if you could go faster, you would have more kinetic energy. You get what I'm saying? So this is actually the maximum speed right here when it passes through equilibrium. Okay? Now, at this moment in time, we have that the spring is partially compressed and that the mass is moving to the left with a moderate speed. So we have both elastic potential and we have kinetic. Then here at full compression, we have no there's a really good question. It's in the chat. It says, with this situation, would the amplitude gradually decrease until it reaches equilibrium again? We are considering a completely frictionless simple harmonic motion. So if it's completely frictionless and there's no air resistance, it just keeps going back and forth forever. Okay? Next week, we're going to talk about the presence of friction. And so if you do have friction, then some of the energy is going to become heat with each period that is completed. Okay, so you lose amplitude with each successive vibration. That's a really good question. Okay, so Here we have that the mass is fully compressing the spring, so we have no kinetic energy. If we did have kinetic energy, it would compress the spring even more. All right. And so we have the energy is all potential, 1/2 K times negative A squared. Negative A quantity squared is just the same thing as A squared. Okay. And then here we have, again, some compression and some motion. So we have 1/2 kx squared plus 1/2 mv squared. Here we have all kinetic energy, so we just have 1/2 mv max squared. Here we have some extension of the spring, some speed, so we have 1/2 kx squared plus 1/2 mv squared. And then here we have the spring is fully stretched, so it's all elastic energy, 1/2 k a squared. Okay? Now, because energy is conserved for the mass spring system, and we're assuming that no heat is being generated, no energy is being dissipated to heat, all of these expressions have to be equal to each other, because these are just, we're calculating the energy at different moments in time, so all of these are equal to each other. Okay? So the energy is the same at each of these moments. And by the way, this last moment, because it went back and forth, this is at a full period. This is after one full period of time. Okay? So let's go ahead and make some observations about this really quick. Okay? So the first observation is just the energy. The energy consists of elastic potential and kinetic. All right? And depending on when in time we choose to evaluate the energy, we could find that at a particular moment we have both, or we could find that we have all kinetic if it's passing through equilibrium, or we could find that it's all potential if it's at one of its extreme points. Okay? But all three of these are equal because energy is conserved. So we could actually set any two of these equal to each other. We could say 1/2 kx squared plus 1/2 mv squared equals 1/2 mv max squared. We could say 1/2 kx squared plus 1/2 mv squared equals 1/2 k a squared. Or we could say 1/2 k a squared equals 1/2 mv max squared. All right? So, yeah, the energy at any two moments in time, we compare them, they're going to be equal because energy is conserved. All right. So second observation is that the system has a constant energy, but the energy is being exchanged between elastic potential energy and kinetic over and over again. Okay? So in fact, you could view simple harmonic motion as just an exchange of kinetic to potential to kinetic to potential to kinetic to potential over and over again in perpetuity. Okay? So we can see here we have all potential. Here we have the exchanges happening, so we have some kinetic and some potential. Here we have all kinetic. Here we have the exchange is happening this time in the reverse direction. Kinetic to potential, all potential. Potential to kinetic, all kinetic. Kinetic to potential, all potential. Okay? So the energy is changing from one type to the other, but the total amount is changing, is constant. The system has its maximum kinetic energy as it passes through equilibrium. Which is x equals 0 in this case. At that instant, it has no potential energy. Okay? And so why doesn't it stay at equilibrium? Well, if you are at equilibrium and you have no kinetic energy, then you're just going to stay there forever. But it doesn't have zero speed at equilibrium, so its inertia carries it through equilibrium. The system has no kinetic energy at the extreme points. The extreme points, you will recall, are x equals plus or minus an amplitude. So it has its maximum potential energy. Okay? So we are going to go into more depth with these relationships, in particular with these equations, on Friday. So I just want to check in with you guys in the Zoom room, make sure everyone fills out attendance and so on. So that's my lesson for today, and I will see you in the Zoom room.